the main formulas for mean or average, range and standard deviation, which will be used in statistical quality control. Six Sigma, right? Six Sigma. An important trend in manufacturing operations as well as in business and service industries is the concept of Six Sigma. Six Sigma is a set of statistical tools based on well-known total quality management principles to continually measure the quality of products and services in selected projects. Now again, in industrial engineering, there is a full elective course on Six Sigma, right? So you can go there and you know the rules in the university. In the final year, you have to take 4 elective courses, and 3 of them have to be in your major area, and 1 you can take outside the major. So even if you are doing chemical engineering, you can take 1 course from industrial, mechanical can take 1 course from wherever, right? So anybody can take Six Sigma or other courses and so forth. Let me define what is written below, and then we will come back to Six Sigma. Control charts. Control charts are certain charts which are based on daily production, weekly production, monthly production and so on, where we use some control limits. Control limits. So of course there will be an upper control limit, UCL, and a lower control limit, right? Remember, when we were talking of tolerances, there is the mean dimension, there is the actual dimension that we want, and upper tolerance, lower tolerance, right? So this is upper control limit based on mean and lower control limit based on mean. How is it defined? X bar plus 3 sigma, the mean value plus 3 times the standard deviation. X bar minus 3 sigma, the mean value minus 3 standard deviations. So you see, plus 3 sigma minus 3 sigma. So total tolerance of 6 sigma. So this is it, 6 sigma. This has been done hundreds of years of research, and then they found out that, you see, you are actually doing some production. You are actually measuring the dimensions, the diameter of something, the diameter of a rod that is produced per day, right? The thickness of a plate that is produced per day, hundreds of pieces and so on. So you are and doing it in batches, and you are doing it in batches of 10, 10, 10, 10, whatever, 12, 12. And you can find the mean from each sample, right, of 10 pieces and the standard deviation. Now they found out this unbelievable thing, that if you put the tolerances as X bar plus 3 sigma and X bar minus 3 sigma, then 99% of the pieces will be within the tolerance. Less than 1% will fail, for example. But this is unbelievable. This is unbelievable, that rather than trying to think by some other experience and this and that what should be the tolerance limits, you decide based on actual math and science statistics, that do sampling, take many samples. The more samples you do, the better the result. You have the mean value, which is of course the design value. This should be the dia, and plus minus some tolerance. So plus 3 sigma minus 3 sigma. You put these tolerances and then you will. So this is, we will not go into the details of all of that, but that is why it is called the Six Sigma approach in production and quality control and so on. But of course, then you should know the standard deviation beforehand. You actually do not do it, so you do this new formula. X double bar is the grand average or average of average. What does this mean? You take a sample of 10 pieces, you make an average. You take another sample of 10 pieces, you find another average. You take another sample of 10 pieces, you find another average. So however number of samples you have tested, 10, 10, 10 each time, this is the average of the average. This is the average of the average. This is X double bar. And if there was only one sample of 10 pieces, then this is maximum, this is minimum. You find a range. You find range from first sample of 10, second sample of 10, third sample of 10. When you find the average range, then it is R bar, right? So these are two new numbers. X double bar is the average of averages from different samples, and R bar is the average of range from different samples, right? What is this A2? What is this D4? What is this D3? What is this small d2? These are values which we will show you in a table shortly. So they are constant numbers, don't worry about them, right? So now you know how to define the upper control limit on x bar and lower control limit on x bar. X double bar plus a2 r bar, x double bar minus a2 r bar. Instead of upper control limit, lower control limit based on x bar, we can define it based on range also. So upper control limit for range is d4 r bar. Lower control limit for range is d3 r bar. And if you want to find a standard deviation from these readings, then it is r bar upon d2. R bar, remember, is from all the samples that we have tested, first, second, third, and so forth, right? And A2, D4, D3, small d2, these are values which we will provide based on a table. That will come later on, but right now let us talk of control charts, because we were talking of control charts before, right? So this, for example, is a control chart based on x bar. So this x bar is the mean value, and every time you take a sample, say for example 5 pieces, so you take 5 pieces, take their average value, it comes out to be this. Next 5 pieces, take the average, it comes out to be this. So this is not the value of one, this is the value of the average from one sample. So if they are taking 5, 5, 5, then every half an hour, every 1 hour, they are checking 5 pieces. So if you see, right, this will be x bar and a2r minus a2r and so on. So this is the upper control limit, this is the lower control limit. If from all the samples that you test, all the average values are well within the UCL and LCL, then it is called to be in good statistical control. The process is in good statistical control. If it is like this, if all the values are close to here, all the values are close to there, then it is bad. If some values are outside the limit there or outside the limit here, then it is not in control, right? Similarly, we can do this based on R bar. This was based on X bar. So on R bar, the upper control limit, lower control limit, and again, from each sample of 5 pieces or 10 pieces or whatever, if the average R, right, if the R from one sample, second sample, third sample is within the upper and lower control limits, then the whole process is in good statistical control. So we measure these values, quality control inspectors are working, or there is an automated measurement system, and we are testing batches of 5 pieces or 10 pieces or 12 pieces. We are doing those measurements every 1 hour, every 2 hours. It depends on the company's policy, and these are the control charts to keep a continuous eye per day, per week, per month of how things are going wrong or not. This is the table, right? This is the sample size. 2 pieces, 3 pieces, 4 pieces, how many are we testing each time, and then A2, D4, D3, D2, the values, right? So this is it. So if you know the sample size, remember sample size does not mean how many samples you have tested. It means that in one sample, how many pieces are you testing? You are testing it now and again and again. So within a day, maybe you're testing 8 times. That is not the sample size. That is the number of samples, right? Sample size means that in each sample, how many pieces are you testing? 5 pieces each time, 10 pieces each time. So based on that, you can find these constant values which were there. So therefore, the calculations are very, very, very simple. Right? So with this now, do this, calculate the control limits for averages and ranges for the following. Number of samples is 7. Now here, right, number of samples is 7 means number of samples each time, right? You are right. So this is actually a wrong way that you are writing it. They should not have written number of samples. They should clearly write sample size. And the grand average is 50, the R bar is 7, right? So the formulas are there. As I always tell you that please stop here, pause the lecture, take pen, pencil and so on. Go back to the previous page, see the formula for upper control limit, lower control limit based on X bar, upper control limit, lower control limit based on R. The values are given. This is a small n, sample size. Grand average means X double bar. R bar means R bar. So these are there, then nothing else is there, just put in the formula and you see the upper and lower control limit values, right? So yes, the upper and lower control limit values, it is x double bar plus a2 r bar, x double bar minus a2 r bar. So for a sample size of 7, we go to the table and find a2 is this much, d4 is this much, capital D3 is this much. So for a2, you put these two values, and x double bar is already 50, right? So 50 into this and sample size, right? So, and just get the values, and r bar is 7, Similarly, UCL for range and LCL for range, D4 and D3. So just put the values of D4 and D3 and find the numbers, right? So this is the upper and lower control limit based on the mean value. This is the lower and upper control limit based on the range. And this is how you divide it. If you want to be very strong in your judgment, then you don't do it only for means, you can do it for means and ranges. And both ways, if it is under good statistical control, then you are very happy with your process. Otherwise, if there is any problem, then you look into it. As an example of real process, now you see this is some thing going on, right? So they are measuring average diameter, and this is not average, right? This is average from one sample of 7 or whatever. So this is the x bar. Now all these values are very nice. But here something started to happen. It started to increase until we noticed this value, and then it came down, right? So it went out of control. In this region, it is in good statistical control. In this region, it is in good statistical control. But here, the statistical control is gone and we have a bad piece. As an example, what they have written here, you see, suppose it is a machining operation. We are doing some lathe machine operation. The tool is there. It has produced 1 part, 2 part, 3 part, 10 parts. After some time, the tool will become not sharp, unsharp, dull. So in routine practice, they have an idea that after producing 10 parts, change the tool, cutting tool. If the operator forgets it, then the cutting tool is going bad. The cutting edge is not sharp anymore. So if it does not replace the cutting tool in the proper time, then it goes out of control. And suddenly somebody realizes, oh my goodness, we did not change. So suddenly you change the cutting tool and it is back to normal. In this one, for example, almost all the values are above. So because of some reason, it is not close to the mean. It is all close to the upper mean. So something has happened. You try to find out the reason, right? Maybe the tool is dull and maybe nobody is looking at it. The operator is not bothered about it and so on. Here it is in good control and then suddenly it goes bad and then it remains bad. Nobody wants it, right? So you see, if somebody is monitoring, then even if something goes wrong, only 1 or 2 pieces go wrong and then you come back. But if it is not monitored, somebody has, the person who should be monitoring this has gone on a tea break, and instead of 5 minutes, he has gone for 2 hours. So if there is something bad, it keeps on going bad, right? So control charts, because they are a record, they give you a brilliant control per day what is happening, per week what is happening, per month what is happening. And then we can try to go back and trace the reasons that why this happened like this, right? And it depends, of course, on the type of industry that you are in. If you are in a workshop, it is a reason like, say, the tool has not been changed. But for example, you are in a workshop, I've given this example earlier. Outside, a heavy truck is going. Now, heavy truck, there is a big vibration, and lathe machine and so on is running. And for all the time that the big truck is passing from outside, all the values are now wrong. And then it goes back again, and people do not understand what is happening, right? So all that will be quality assurance then. That quality control people record what is happening. And if this record is there, then later on you look at it and you try to find out the reasons, and then you remove the reasons.